Hi friends, welcome back. In the previous session, we have started with the Fourier transform. In that, we have seen two important properties of the Fourier transform, which are nothing but time reversal property and linearity property. Time reversal and linearity property. We have seen some questions regarding the time reversal property, but let's go for the linearity property now. So in the linearity property, I said suppose if x1 of t is a function having x1 of omega, if x2 of t is a function having x2 of omega, then x1 of t plus x2 of t having Fourier transform, which is nothing but x1 of omega plus x2 of omega. So this is what we have seen already in the linearity property. So let's solve some questions based on this one. So let's take an example which is like this. Let's say x of t is equal to e power minus a mod t. E power minus a mod t, where a is positive. Where a is positive. For this function, I have to calculate what is a Fourier transform. So for that, what we can do, let's say, can I write this function into sum of two functions? What are those sum of two functions actually? So if I say, if t is positive, then it is going to be e power minus at. If t is positive means, can I multiply the function with u of t? Then it is going to be e power minus at u of t. What if t is negative? Then it is going to be minus t into minus a. This is going to be e power at. If any function is existing only for negative values of time, that means I can multiply with u of minus t. Then here I can write e power at u of minus t. E power minus at u of t. For these functions, I have to apply the Fourier transform. Let's see. By applying Fourier transform, what I am going to get? For this function, Fourier transform is 1 by a plus j omega. For this function, 1 by a minus j omega. Now, if I multiply it, LCM is a square plus omega square. Then this is a minus j omega plus a plus j omega. J omega get cancelled. Then finally, this is 2a by a square plus omega square. So this is what the Fourier transform for e power minus a mod t, having Fourier transform 2a by a square plus omega square. So it is also standard result, you have to remember. Take it. Take it. Suppose if I have given a signal, next signal, x of t is equal to e power minus at u of t plus, instead of plus, if I take minus here, e power at u of minus t. First, if I say, can you draw the signal x of t, how it look like? So if I draw the signal x of t, it will look like this. With respect to t, e power minus at u of t, because it is a right sided exponential decaying, here it is 1, e power at u of minus t, so it has to look like this, but we are having a minus sign, so it has to be reversed, so that it will be look like this, growing exponential plus 1 minus 1. So there is a jump. which looks like this. For this function, I want to calculate what is x of omega. So I can apply x of omega is equal to, for this function, 1 by a plus j omega minus, for this function, 1 by a plus j omega. Then this is going to be a square plus omega square is the LCM, a plus j omega, sorry, a minus j omega minus of a plus j omega. So here a get cancelled. Finally, what we are left with is minus j 2 omega by a square plus omega square. So this is what the x of omega for this function. Why we require x of omega for this function, you can understand. First take down this, then we will see what is the application of this function. Okay, take it. So listen, what is the application of this function? Why we have intentionally taken this function is, let's take x of t signal. If I put a tends to 0, if I take a limit where a tends to 0, if a tends to 0, this will become u of t minus u of minus t, which is nothing but signum t. So by taking the limits for a, then I can get a signal which is nothing but signum t. And if I take a tends to 0 here, then that is nothing but the Fourier transform for the signum function. So first of all, you may get doubt. So why we have to go in this procedure? Why can't we calculate the Fourier transform for signum function directly? For signum function, we cannot calculate the Fourier transform directly because it is a power signal. I already told you, power signals, we have to go for indirect methods to calculate the Fourier transform. So this is the method what we are using. Now let's take limit a tends to 0 x of t, limit a tends to 0 x of t. So limit a tends to 0 x of t, that will become u of t minus u of minus t, which is nothing but signum t, which is nothing but signum t. For this one, I have to calculate the Fourier transform. Then what we have to do? Limit a tends to 0 minus j 2 omega by a square plus omega square. So in this, if I place a is equal to 0, then finally I am going to get minus j 2 omega by, this is going to be omega square. Omega get cancelled. Finally minus j2 by omega. So bring this j to denominator, then this will become 2 by j omega. So this is what you have to remember finally for a signum t function. Signum t function, we are having Fourier transform 2 by j omega. 2 by j omega. So this is what you have to remember finally. Okay, take it. From this, we can calculate what is the Fourier transform for step function. So I want to calculate what is the Fourier transform for step function. Step function can be written as 1 by 2 plus 1 by 2 signum t. You might remember how I have written this. Actually, signum t can be written as the 1 plus 2 u of t. So that 1 minus 2 u of t kind of thing you can write. 2 u of t minus 1, 2 u of t minus 1 we can write. Or we can write u of t which is having even part and odd part. So in that manner also we can write u of t like this. So once we got u of t like this, we have to calculate the Fourier transform for this. How we can calculate the Fourier transform for it? Let's see. If I apply Fourier transform, for 1 we know the Fourier transform is nothing but 2 pi delta omega. So 1 by 2 into 2 pi delta omega. This is the Fourier transform for 1. Next, 1 by 2. For a signum function, just now we have calculated the Fourier transform, that is nothing but 2 by j omega. So 2 to get cancelled, we are left with 1 by j omega. 2 to get cancelled, finally we are left with pi delta omega. So if I jumble them, then we are going to get 1 by j omega plus pi delta omega. So this is the Fourier transform what we got. So you have to remember it is a standard result. For step function, the Fourier transform is 1 by j omega plus pi delta omega. 1 by j omega plus pi delta omega. So this is the Fourier transform for step function. You have to remember. Okay, take it. Because we came to know u of t, can you calculate what is a Fourier transform for u of minus t? From the time reversal property, I can simply say in the Fourier transform, omega has to be replaced with minus omega, because here we have replaced t with minus t. So if I replace omega with minus omega, this is going to be minus 1 by j omega plus pi delta minus omega. But delta of minus omega is becomes delta omega only, because impulse function is nothing but an even function. So I can say for this one, the Fourier transform is minus 1 by j omega plus pi delta omega. Pi delta omega. So for u of minus t, this is the Fourier transform. So let me give you summary what we have done till now and what we have to remember. So the important results you have to remember. Let's see those important results, what you have to remember. The first and foremost thing, suppose delta t is there. What is the Fourier transform for it? 1. For 1, what is the Fourier transform? 2 pi delta omega. Next, e power minus at u of t. Here we got 1 by a plus j omega if a greater than 0. Next, e power at u of minus t. For this we got 1 by a minus j omega. Next, e power minus a mod t. For this we got 2a by a square plus omega square. Next we got for signum t. Signum t, this is 2 by j omega. In the same way, u of t we got 1 by j omega plus pi delta omega. Pi delta omega. In the same way, we got u of minus t also. Minus 1 by j omega plus pi delta omega. Because impulse function is an even function. Even though if I replace omega with minus omega, it won't make any difference here. So these are the formulas you have to remember. Just take it. Symmetry property. As we have seen in the Fourier series, because Cn, that Fourier series coefficient is exhibiting conjugate symmetry. In the similar manner, x of omega is also exhibiting the conjugate symmetry. So I will give you directly the result here. So what is x of t nature, what is x of omega nature? Just you can remember them as in the case of the Fourier series. So let's see, x of t, x of omega. If x of t is real and even, then x of omega is also real and even. Suppose if it is real and odd, then it is imaginary and odd. Imaginary even, imaginary even, imaginary odd, then it is real odd. Suppose if it is real and neither even nor odd, then it is going to be a complex function and exhibit conjugate symmetry. And exhibit conjugate symmetry. I told you how to remember these things, because if you get even, even, odd, odd, even, even, odd, odd. But only thing is, if it is even, real nature will become real nature only. If it is odd, then real nature will become imaginary. So this is what you have to remember. So, and we have seen these things in the Fourier series also. So I am not stressing here much, so you can remember them easily. Okay, take it. And if you see one example, let's say signum t. Is it an even function or odd function? It is an odd function. That's why we are getting imaginary and odd. So it is a real and odd. It is nothing but imaginary and odd. So that's what here we have, real and odd having imaginary and odd. Suppose if I say this function e power minus a mod t. So if you look at this function, so how it look like this function e power minus a mod t? So this is going to look like this, e power minus a mod t with respect to t. So it's a real function and even function. So if it is a real and even, what is x of omega we are going to get, which is nothing but again real and even. So even if you take omega plus omega or minus omega, it won't make any difference. So I can say this is real and even only. So I hope you understood what I am trying to say. So these are the functions in x of t, the nature of the signal in the x of t, and in the frequency domain, this is the nature we have to remember. Okay. Question number 4. A signal x of t is shown in figure, is as shown in figure. Then its Fourier transform is, this is what x of t is shown. X of t. Options: option A, real and even function of omega. Option B, real and odd function of omega. Option C, imaginary and even function of omega. Option D, imaginary and odd function of omega. So which of the option is correct for this function x of t? So we just have to understand what is the nature of x of t. Once we know the nature of x of t, the Fourier transform nature can be directly said from the given table. So let's see. X of t. Is it a real function? Of course, we are having only between the value of x of t only between -1 and +1. So I can say it is a real value only. And if you observe carefully, if I fold it, I am going to get like this. If I fold it, I am going to get like this. That means it is a negative of that previous signal by folding it. That means by folding it, I am getting the negative signal. That means it is an odd signal. So I can simply say it is a real and odd signal. So if it is a real and odd signal, x of omega must be imaginary and odd function of omega. So I hope you understood. X of t is a real and odd. If x of t is real and odd, x of omega is a imaginary and odd function of omega. So this is the way we have to say what is the nature of Fourier transform. Take it. Question number 5. A differentiable non-constant real even function x of t has derivative y of t, and their Fourier transforms are x of omega and y of omega. X of omega and y of omega. Which of the following is true? Then which of the following is true? Which of the following is true? Options: x of omega and y of omega both are real. Both are real. Option B: x of omega is real and y of omega is imaginary. Option C: x of omega and y of omega both are imaginary. Option D: x of omega is imaginary and y of omega is real. Okay. I hope this question is over. Okay. Observe here, they have given about the function x of t. What is x of t? Real even function. X of t is a real even function. and y of t is the derivative of x of t, then what is the nature? So let's say given x of t function which is a real and even, for this function what is x of omega nature? So we have seen from the table real and even function is having real and even function only of omega. Now what is y of t? Which is nothing but dx of t by dt, that is nothing but derivative of the x of t, Now you tell me, if I derivate a real and even function, what I am going to get? That is nothing but real and odd function. From the properties of even and odd function, so properties of even and odd function, what are they saying? Properties of even and odd. What is it saying? If I differentiate a even function, then the resultant is a odd function. If I differentiate an odd function, then the result is going to be even function. So this is what we came to know. So from this I can say, because it's an even function, if I differentiate that, I am going to get real and odd function. So I am going to get real and odd function. For real and odd function, what is y of omega? So from the table, real and odd function is having, it is nothing but imaginary and odd. So it is nothing but imaginary and odd. So I can simply say x of omega is a real function, whereas y of omega is a imaginary function. So which option is going to be correct? Option D. X of omega is real, y of omega is imaginary. Take it. Next property, time shifting property. What is time shifting property saying? Suppose if a signal x of t having Fourier transform x of omega, then what if I take x of t minus t naught? Then this is going to be x of omega e power minus j omega t naught. So shifting here leads to exponential multiplication in other domain. That means shifting in time domain leads to exponential multiplication in the frequency domain. In the similar manner, suppose if I take x of t plus t naught, then we are having x of omega e power j omega t naught. So this is the Fourier transform. Let's take one question. Question number 6. Find Fourier transform of, FT means Fourier transform of x of t is equal to e power 3t u of minus t plus 2. For this function, we have to calculate the Fourier transform. Okay. So if you observe carefully, it is having so many properties. That means, let's say we have to apply different properties here, not the single property. Then once we came to know we have to apply the different properties, then don't apply all at a time. Apply one by one. What do you mean by that? So let's say start the analysis or start the solution from what we know. That means what we know. So in this function, let's say, suppose if I have given you e power minus 3t u of t. Do you know anything about this function? Yes. So for this function, we know that the Fourier transform is nothing but 1 by 3 plus j omega. This is what we know. Now for this function, what are the things we have to apply so that we can get this one? So let's say we got t plus 2 here. So if I apply time shifting property here, this is nothing but e power minus 3 t plus 2 u of t plus 2. So in this case, I have shifted by plus 2. That means we have to multiply this function with e power j omega 2. E power j omega 2. That is nothing but e power j 2 omega. So with this function we have to multiply. Now, if you observe carefully, this is nothing but e power minus 3t, e power minus 6 u of t plus 2. So in this one we are having extra e power minus 6. Bring it this side. So this is going to be e power plus 6, e power 6, e power j 2 omega by 3 plus j omega. 3 plus j omega. Up to this part it is okay. But here I have to get 3t. Here we have to get u of minus t also. U of minus t also. Can I simply replace t with minus t? That means I am applying the time reversal property. So if I apply time reversal property here, this is going to give you e power 3t u of minus t plus 2. E power 3t u of minus t plus 2. So if I apply time reversal property, what it is going to do in the Fourier transform? There we have to simply replace omega with minus omega. So if I do that, this is going to be e power 6 e power minus j 2 omega by 3 minus j omega. So this is the Fourier transform for the given function, which is nothing but x of t. For x of t, this is the Fourier transform we are going to get. Clear? Take it. Function, we already done that. Sampling function. So we already done that, but still I am doing it here because so that it is going to be more familiar. Let's say sampling t. Sampling t. Sampling t function is nothing but sin t by t. Sin t by t. So how we can write this function graphically with respect to t? So it looks like this. So this is the function how it look like. At 0 it is going to have the maximum value. Next at pi, 2 pi, 3 pi, minus pi, minus 2 pi, minus 3 pi, like that. For these values it is going to be 0. This is what sampling function. In the similar way we are having sinc function. Sinc t is equal to sin pi t by pi t. Sin pi t by pi t. So graphically it looks exactly same as sampling function, but only the difference is where it will become 0. At 0 its value is again 1. Now if I take t value is equal to 1, 2, 3, like that. That means at integer values we are going to get 0. At integer values of time it is going to be 0. And we are having a relation between sampling and sinc function. Suppose if I take a sampling t, this is nothing but sinc t by pi. At the same time sinc t is equal to sampling pi t. Sampling pi t. So these are the things what we know. And one more thing, suppose let's say a function sin at by bt is given to you. For this function, what is the sampling function? I told you the t coefficient is a here, the t coefficient is b here. Then we are going to get a by b sampling at. At the same time, this is nothing but a by b sinc at by pi. At by pi. Next, suppose there is a function sin at by pi t. How can you write this one as a sampling function? I told you the coefficient of t is a here, the coefficient of t is pi here. So we can write a by pi sampling at. A by pi sinc at by pi. So in this way we can write. Okay, so this is already we have done it, but still you can take it so that it is going to be more familiar because we are using it here now. Okay, take it.